Good evening, everybody. Welcome to the Mixer meeting, um, August the 5th. And before we get started, first thing we're going to do is read the disclaimer. Please note that all our meetings are recorded and made available to the public for viewing on our YouTube channel. By participating in the meeting, it is understood that you have accepted these terms. So before we get started, we have a couple new people. Uh, JP, why don't you just go ahead and talk about your ham radio short form?
Sure. Yeah. JPVA3FWE. I just got my license in February, and then I got my advanced in March. I think this is probably something that is relatable for a few people here, but the advanced was easier than the basic because I knew the electronics and I didn't know the protocol.
Regulations.
Yeah. But yeah, I've been doing a bunch of electronics repair and stuff. Previous to this, for 15 years, I was a game developer, and that ended abruptly. So here I am, having a lot of fun.
And Glenn, short form about yourself?
Hi, my name is Glenn. I'm in Uxbridge. I've been in ham for quite a while, since the 80s, and I do a lot of experimentation at home, and I'm interesting to join the group. Thanks.
Very good. Okay, so on the agenda tonight, so our mixer meetings, the first Wednesday of the month, it's not a formal. Uh, sometimes we'll do a presentation, we'll have question and answers, what's on the bench, all that type of stuff. But tonight, Dave's going to talk about decoding I squared C, and then after that, we'll do whatever. So if you're ready to rock, Dave.
Doesn't look like they saw that.
Okay, perfect. Tonight I'm going to talk about decoding I squared C. This is an introduction. It's not a detailed presentation about I squared C. It's purely about how to decode I to C using a scope, using your normal scope. And I've got a couple of variations of it, which I'll go through in a minute. But this came about because Peter was posting a bunch of messages about, he was having some I squared C problems, and he was asking me if I was able to have my signal and scope decode I squared C, and I was able to do it. And he said, well, he spoke to a few people, and the people he spoke to was not able to get it to work. So I'm going to show you how to make it work in this presentation. So this is not an I squared C tutorial. Now it's written I2C, but it's I squared C. Okay, but typically everyone writes it as I2C, but it's I squared C. So it's not a tutorial. I'm not going to go through how I squared C works and how to use it and how to configure it and all that stuff. I'm not doing that. I'm just going to be showing you how to decode it with the scope, how to do some basic troubleshooting on it. So here's what I'm going to talk about. I'm going to talk, first of all, about, give you some fundamentals, talk about the physical layer, the bus itself. And this is very, very important, because if you don't understand this, decoding will not make sense. There's only, I've got about 3 slides here. Then I'm going to show you my test setup for how I made my captures. I'll show you the hardware setup, the software setup, and basically, again, how the test bench or the test hardware I'm using and software I'm using to actually do the decode. So then I'll show you how to do a decode with just a simple sample and hold. Any scope that can do a sample and hold, I'll show you how to decode it, and it's done using a manual decode. Then I'll show you how to do an automated decode using the Siglent scope. This is the scope many of us have. Some of us have the 100 megahertz, but I think the majority of us have the 250 megahertz scope. There's no difference between 100 and 250 megahertz. It's going to decode I squared C, because I squared C is running a fraction of that bandwidth, like 400 kilohertz, 1 megahertz. So having a 100 megahertz versus 200 megahertz scope doesn't matter. Then I'll end it with showing you a simple logic analyzer that I picked up for $10 and how you could use that. So most of the information I got from doing this presentation, and also how I learned about doing I squared C, came from the user manual. Siglent has got everything in the manual, exactly how to go and decode I squared C. There is a couple of little gotchas which I'm going to show you about. I'll share with you, because even what they say to go and do, it won't work unless you address these couple little gotchas. And of course there's the bus specification. The original bus, came out in 1982 by Philips, and I've got here 2 specifications. I think this is the original Philips spec, and this is probably updated Philips spec, and I quoted some information here about the bus. The key thing to know that it's a 7-bit bus. It's a 7-bit address bus. So your addressing, the addressing bits is 7 bits. So let's go through some of the fundamentals now. This won't hurt at all. Just a little bit of brain surgery. But here's the physical layer. So this is very, very important that you understand this. So the bus is composed of 2 lines, and you'll see sometimes it referred to as a 2-wire bus. There's 2 lines. One is the clock, SCL, serial clock, SCL clock. That's the clock line. And the SDA line, that's a serial data line. This is a half duplex bus, meaning only one device can communicate on the bus at any one time. Full duplex means both devices or multiple devices can communicate at the same time. This bus, only one device can communicate at any given time. The bus, it's what's called an open collector, open drain bus. It's a high Z bus. Same, my Z80 computer that I built. Same thing. It's a high Z. And why is it a high Z? Because if you look at the devices, all the devices have is a FET or a transistor that shorts the bus. That's all that the devices does. So you've got these pull-up resistors that pull up the line to 5 volts or 3.3 volts, or whatever your voltage is that you're powering the devices at. So these are going to pull the devices up, and the devices can only short it. It can only pull it to ground. Now, if these devices are open, they're open collector or open drain, in this case open drain. These are all FETs, open drain, so it's high Z. So you've got a resistor here and then high Z here. So obviously it's going to float up, it's not going to pull down to ground until you pull this, you enable this to pull it to ground. And bus lingo, you'll see a lot of times they call what asserting the bus. When you assert the bus, you're pulling this line to ground. So you're asserting the bus. So this bus, if you look at the bus, it can be modeled from a resistor and a capacitor. The resistor is the pull-up resistor, and the capacitor is the bus capacitance. So if you go back here, this pull-up resistor, that's the resistor, and this bus, it has inherent capacitance. As with most buses, it's got some kind of capacitance. So that forms an RC network. So when the device pulls the bus down, remember here, when the device asserts the line, so it turns on this FET, shorts the line, all it's doing is shorting the capacitor, that bus capacitance, shorting it to ground, and it drops immediately. And it doesn't matter what size resistor or what frequency you've got, doesn't matter, it pulls it automatically to ground because you're shorting that capacitor. But once you release it, so once this device releases it, it pulls it to ground, asserts the line, releases it, now that capacitor has to charge through that resistor. And that's why you're seeing this coming up. So depending on your size of your pull-up resistor, you could have it coming up fast, or you could have it coming up slow, or you could have it really coming up slow. And your choice of your pull-up resistor could cause your bus not to work. Now, you have to use proper pull-up resistors. Now, most Arduinos, they may have a 20 to 50K pull-up resistor embedded in the device, which is probably too large to pull this pull the network up, because it's going to charge very slowly and you're going to end up with a rounded edge. So typically you would need to put either a 4.7K, something around a 5K for a relatively low speed or low capacitance bus, or from a 1.5 to like a 2K for a higher speed or a higher capacitance bus. And the speed of the bus, typically most devices run at 400 kilohertz, but you could run this bus at 1 megahertz or 3.4 megahertz depending on the device. Now, it's really important you not make this too low, because let's just say you put 50 ohms here. So let's just say you put 50 ohms or 10 ohms here. Okay? So when this device shorts it to ground, all that current that's coming through that resistor has to go through this device and you're going to burn it out. So it's important that you don't choose your resistors too small. Can you guys hear me okay? Are you still there?
Yeah, no problem.
Okay, good. Okay, so we just talked about the physical layer. Let's talk about the communications, the way the communications are done. This is really, really important if you're decoding it on a scope and you don't have the scope decoding it for you. You have to do it manually. This is very, 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 very important. So when these lines are floating high, they're floating high, okay? How does a device know that, okay, someone's communicating? So what happens, they do this start condition. And the start condition is such that the clock pulse is high. When the clock pulse is high, you pull SDA down when it's high. And that signals all the devices, hey, I'm starting to communicate. Conversely, you do the opposite when the clock line is high and you deassert the SDA line, you let it come back up, and once it comes back up you've got a rising edge during a high, that is a stop condition. It says, okay, I'm stopping communications. So here you've got a falling edge during a high clock pulse, and you've got a rising edge, and that's a start and stop. Now, as I said earlier, and I'll talk about it a little bit more, but there's 7 bits, 7 clock pulses, which are used for the device address. The 8th clock pulse is used for read-write, that's telling you read-write, and the 9th clock pulse, this is very important if you're going to be decoding this, this is telling you whether you've got an ACK or a NAC. So what happens during that 9th pulse, that clock pulse, if a device pulls SDA low, so the SDA is low during that 9th clock pulse, so during that clock pulse, here it's low, that means ACK. And if the device doesn't pull it low, it's a NAC. The reason they do this is because if, let's just say there's no devices here, there's nothing. So your Arduino or whatever starts talking on the bus, it sends out a whole bunch of data, it sends out a whole bunch of data, there's nothing there. So on the ninth clock pulse, this line will automatically float high. There's no device to pull it down, so it'll be a knack. And that's how the device knows nothing's there. That's how, by the way, that IC2 scanner that you use, that's typically how it works. So the ACK, basically, it's a successful communication. Device pulls it down, says, I heard you, you're talking to me, I hear you, let's go on. A knack means nothing's there. So if you're decoding this with your scope, and that 9 clock pulse, you're not seeing it pull down, then that's helping you troubleshoot. So just to kind of walk you through how this works. So you've got 7 address bits, so 1, 2, 3, 4, 5, 6, 7, and you've got 7 pulses. This diagram starts at 0. I don't know, you can't have a 0 clock pulse. It starts at 1, so I usually start at 1. So, you have 7 clock pulses, 1, 2, 3, 4, 5, 6, 7. So right here, those 7 clock pulses are clocking the address. So when the clock pulse is high, and if the data is high, that's a 1. If the data is low, it's a 0. Only when the clock pulse is high, it looks at the bus. So in this case, you got the 7 address bits, then the 8th bit, remember I said that's a read-write bit? So you've got the read-write bit. 8th clock pulse is the read-write bit. Here it shows as 7, but it's 8. 1, 2, 3, 4, 5, 6, 7, 8. It's the 8th clock pulse. And if it's high, it's saying I want to read from the device. If it's low, in this case, see it's low. When this clock pulse is high, it's low, so that's a write. Then saying I'm writing data to the device. Then the 9th clock pulse, during when that clock pulse is high, if the data line is low, i.e. a device has pulled that line low, then that's an ACK. If it's high, that's an ACK and it's not working. So there's lots of other I2C, communications. I'm not going to go through it. This is just an introduction. There's clocks stretching, there's repeated start, addressing memory, all that stuff. I'm not going to go through it. I'm just showing you how to do simple decoding. It's an introduction. So here are some common problems. This is what most of the time, if you've got an I2C communication problem, chances are it's probably 80%, 80-20 rule. 80% of the time it's one of these things. You've got the wrong pins. So you've got SDA and SCL mixed up. It's not the pins you think it's supposed to be. It could be the wrong I2C address, because if you send out the wrong I2C address, the device is not going to respond. So you won't see that ACK bit. And could be mismatched voltage levels. But you have to be very, very careful. If you're using a 3.3 bus volt device and you put 5 volts, chances are you're going to blow it unless the device has got 5 volt tolerant pins. Could be incorrect pull-up resistors, because again, if you go to this chart here, if you've got the charging of that capacitor takes too long and you've got this slope, the bus may not register a high long enough for you to see it, or the SDA line may not be high long enough for the device to know it's a 1 or a 0. The bus is too long, too much capacitance. Same thing with incorrect pull-up resistors. They go hand in hand. So if your bus is too long, typically most of the time, you guys can be using a device that uses I2C, and you're not going to be developing it yourself. You're not going to have developed your own bus. So this probably is not going to be an issue. But if you're, wiring up some I2C devices, if you've got too long of wires, you could have some stray capacitor inductance. All kinds of things could happen. You could have ground loops as well. So let's move into how to decode I2C. So here's my test setup. I'm using a Siglin scope. It's a 250 megahertz scope. And I've got Arduino Nano. I've got two pull-up resistors of 1.5K, and it's on the A4 and A5 line. That's the default pins for SDK for the data and clock lines. I'm using a fairly strong 1.5K resistor because I want the edges to be nice and sharp. And for my I2C device, I'm using this LCD backpack. This thing connects to a LCD, and you're able to communicate with that LCD using I2C as opposed to writing parallel bits. And these wires here coming off, the blue and white and the black, are just going to my scope. That's all it's doing. And the address of the backpack is 3F. And channel 1 is connected to A4, which is the data pin, and the clock is connected to A5, which is connected to channel 2. Typo here. Okay, so my software setup, I'm just running this simple little Arduino script. So I'm doing this on Debian 13 VS Code, and I'm using Platform IO. I don't use Arduino IDE. I stopped using that many years ago. It's garbage. I don't use it. And basically all I'm doing is I'm starting up my serial monitor. I start the I2C, and then I just set an address, data. I begin transmission or write the data, and then I check to see if it's successful, unsuccessful communications. Now, by default, the bus is running at about 100 kilohertz. Arduino, I think it by defaults to 100 kilohertz. So if you do a little bit of math here, you know, that's about 100 microseconds per 10 clock pulses. Remember I said it's 9 clock pulses, so let's just say 10. I'm just rounding, make the math easy. So if the scope, you know, the scope has 14 divisions. If you look at my scope, there are 14 divisions. Across, you count all the divisions, there are 14 divisions. So if you set to about 20 microseconds per division, you'll capture 280 microseconds across the entire width of the scope. So the entire width of the scope is going to be 280 microseconds, which will easily capture that data coming in. So what I do, basically I write a byte to a known address, 0x3, see what happens, then I write it to an unknown address, say 0x113, and I see what happens, and here you see I've got a delay of 2 seconds, and it just keeps doing that over and over and over again. And I've got some notes here about how the wire works. I'm not going to go through it. Feel free to go through that yourself by just telling you when the write bit's enabled and when the read bit's enabled and blah blah blah. So now let's talk about manual decoding. So this is going to basically show you if you got the wrong pins or cross pins, you're using the wrong I2C address, you've got incorrect pull-up resistors because you'll see the rising edge will be all gnarly, and I'll tell you you've got incorrect pull-up resistors. Or if your bus is too long, you got too much capacitance, you'll see that. It's not going to tell you if you got mismatch voltage levels, logic levels, unless you know it's a 5-volt bus and you're seeing 3.3 volts, which, by the way, 3.3 volts will work on a 5-volt bus. But if it's a 3.3 volt bus and you put 5 volts, you're probably going to damage something. So unless you know the bus is running at 3.3 or 5 volts, it's not going to tell you that. If it's got a ground loop, I don't think it's going to tell you much about that. But let's go through how to set up your scope. So on my scope, the first thing you do is you hit the acquire button and you set your memory depth to 7 megs. So you're using all available memory in your scope, so it acquires all the data because it can sample really fast and it can collect all the data. So this is one got you that the Siglent documentation doesn't talk about. So next, set your channels up. So again, this is manual decoding. This, I'm not going to show you how Siglent decodes it for you. We're going to be manually decoding this by looking at the trace. Everyone still there? Everyone can still hear me?
Yep.
Yeah.
Okay. So for your channels, you're going to set up DC, full bandwidth, you know, blah, 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 10K probe. Make sure your probe is actually set to 10K. You know, and I've got this set for 2 volts per division. And I set it for both channels the same. Pretty straightforward. Trigger. This is the most important thing. Okay, so remember, channel 1 is SDA, channel 2 is clock. Channel 1 is data, so my channel 1 is connected to data, channel 2 is connected to clock. So you could enable cursors, and here's your cursors, and that helps you to check the timing, or if you can't really tell when the pulse is high, you could use your cursors to go when the clock pulse is high, and you could see what the data pulse is. So you could do that. That's a little trick. But basically, you know, you hit the trigger setup, and what are you going to do? Once you go in here, you're going to do edge. You want to edge, and you want it falling, and you want it channel 1, your data. You want, remember, way back up here, I said that the start condition, where's my start condition chart here? Start condition is the falling edge. So you want to trigger on a falling edge of SDA. Makes sense, right? So where's trigger? Yeah, so you're going to want falling edge on channel 1 to start the capture. Okay? And your trigger level here, you're going to set this to be 1/2 of your Vmax. In my case, it's 5 volts, so you can see my trigger is set to 2.4 volts, which is roughly about half. So you want your trigger to be a halfway because you want the signal to be clearly coming down. You want it to be really clearly coming down, and then you're going to trigger it. The thing here is you want to select single shot. So you want to use single shot, because if you use auto or normal, every time you send data out, this thing's just going to be buzzing. You're not going to be able to see it. With a single shot, it's going to be a sample and hold. It's going to display it and hold. So here's, for example, here's the decode for unknown address. So you could see the clock pulses here, and then you could see the data pulses here, right? And so here what I did was I went and I put little markers so you could actually see what's going on. So here's clearly the start condition. You see the clock pulse is high. There's the falling edge of the data channel, right? So that's a start. So the first clock, you look at that, that's a 0. So it's clock 1 is 0. Here's clock 2 is 0. Clock 3 is high, so that's a 1. Clock 4 is 0. Clock 5 is 0. Clock 6 is 1. Clock 7 is 1. And remember, clock 8 is the read-write bit. So here it is low. So I think low, yeah, it's a write bit. So low means it's a write bit. So we're writing, which is correct, because in my Arduino sketch, we're doing a write. So that makes sense, right? That the write bit will be 0. Then the 9th bit is your ACK. Now, notice during the high period of that clock pulse, the bus is, oh sorry, here's 9. 9 is here. During the high period of that clock pulse, the bus is high, which means it's an ACK. So which means device is not even answering. So you hear your slave is unresponsive. So it's either not on the bus or you've got the wrong address. Makes sense, right? So okay, here's the known address. So all I've done here is I've drawn lines to make it easier. Oh, I didn't show the stop condition. Here's the stop condition here. during the high period of the clock pulse, you've got a rising edge, that's a stop condition. So now here's for a known address. Now one of the tricks here, because this is very difficult to read, even if with these lines it's very difficult to read this, what you could do, even though it's a single shot, you could use your horizontal knob here to zoom in. And you could use your position here to pan. So that's what I've done. And I've zoomed in, so you can see here how much. I've zoomed in to 5 microseconds per division, right? And the trace is shifted 25 microseconds. So it's delayed 25 microseconds. So that's when you use this knob here, that's showing you that delay there. So here now you can clearly see. You can see the falling edge, start bit. You can see data. So it's 0, 1, 1, 1, 1. So 0, 1, 1, 1. Let's go over the next set of bits. So it's 1, 1, 0, 0. Clock 8 is 0, which means it's right. And now look at clock 9. It's 0. This is your ACK bit. So the device has pulled it down. So it's an ACK. So here you've got address 0, 1, 1, 1, 1, 1, 1, which is 3F right, which is correct. So if we go back here, my address of 0x3F is correct. That's what my backpack module is. So that is correct. Now, what follows here is the data, because I also write some data out. So right at this point now, it's writing data out. So it's writing 10. Now it's writing AA. If you come back to here, my data, I'm writing AA. The reason why I chose AA, because AA is 10, 10, 10, 10. It's pretty easy to see on the scope, on a decode. So it's 10. Then you scroll again. Notice my delay. I've panned across. So I could get all the data bits. 8th. And then the 9th bit is, okay, in this case 8-bit is not read-write, it's actual data. So the 9th bit is the ACK bit, and you can see it's being ACKed. And you'll see it in the next slide. But if you look at the data, 10, 10, 10, 10, that's AA, so it's correct. Now notice this little spike here. So what happens is that the master, the device, the Arduino, is releasing the data bus. It's releasing the data bus so the device can pull it low. And here's the 9th clock pulse, and you can see it's low. And you can see this on the next section here. You can see it here. This is just, I've panned it over, so you're seeing 2 bits overlap, but here's that little spike. That's from the Arduino releasing the bus and saying, okay, I expect you to pull it down, and here's the ACK bit. The device pulls it down, good. And then here's a stop bit. You've got the rising edge, or you've got the rising edge here of the data line during a high clock pulse. So that's how you do a manual decode. So let's do an automatic decode now. This is what they don't tell you in the manual. Decoding only works when master and the device, master and slave, the Arduino and the device are communicating. If there's a malfunction and they're not working, the scope will not decode it for you. They must have successful communications. Otherwise it won't work. So for example, and I'll show you, when I use the unknown address, you'll see decode won't work. So basically you set up memory channels same as before. So now, when you go into trigger, this differs now. So you're going to set it to 50 microseconds per division. You're going to send it a little bit longer because you want to see the whole train of pulses. You want to see the address and the data. So you're going to set this a little bit longer so you get everything on the screen. So once again, you're going to select setup, you're going to do single shot, you're going to send this to, again, half trigger and half the voltage, so trigger about 2.4 volts. The type, when you select setup for trigger, you're going to select serial. Then you're going to select the protocol, you're going to click that, push this button, select I2C. For signal, I'll show you in a second what you select, and trigger settings, I'll show you in a second. This is important because you have to do this because you have to tell the scope to trigger on this. Now when you use the decode button here, you have to repeat it again and tell the decode how to trigger the decode. So this, you're telling the scope how to trigger, to hold it on the screen so that the decode can then decode it. So I don't know why these two things are not coupled. You would think they would couple them, but they're not coupled. You have to do them separately. So remember I said for the signal, so this is signal, you select signal, and here, remember on the trigger, you're setting the trigger to be 2.4, so you're telling it now to trigger for I2C decoding to use 2.4. Again, you want it halfway down because you want to make sure that pulse is clearly coming down. It's not noise and you're not getting jitter. It's actually coming down. You have to set it for both the SCL channel and the SDA channel. And for the trigger, remember here I said that you have to set the trigger. Oh, by the way, so for channel 2, you're going to set as the clock. So here you're going to select this button and you're going to select channel 2 for your clock and you're going to select channel 1 as your data. That's very important. So this is where you set your data and the clock. So this, the scope knows that data is on channel 1 and clock is on channel 2. So on the trigger, remember up here I said there's a trigger. Once you push the setup, there's a little trigger setting here. So once you go into trigger setting, this is, you're going to tell it to trigger on a start condition. You're going to say, I want you to start capturing data when you see a start condition. Okay, now you go into decode and you rinse and repeat. You do the same thing all over again. Except here, for decode, you're going to select decode 1. There's a bunch of decodes. You could do multiple decodes, I guess. If you've got multiple devices, multiple conditions, I just use decode 1. Protocols I2C, same thing with signal, same thing with configure. Display, once you put display on, this decode little window comes up. And it shows you the time, and I'll zoom in on that in a subsequent slide and you'll see it. But it's important to remember, same thing you did with setup, you're going to want to do it here. Channel 1 is connected to SDA, channel 2 is connected to clock. So in the subsequent slides I'll go through this. So this is the signal setup, same thing as before. You're going to want to set the threshold. So you're saying, okay, you know that this line is being asserted when it drops below 2.4 volts. For both clock and data, and again, you have to set channel 2 as clock and channel 1 as data. You got to do it again. I don't know why Signal has it, they do it this way, but you got to do it. And then decode, and I'll show you what this is, but basically this is saying decode the read-write bit separately or add the read-write bit as part of the address bit. And I'll show you what this does, but for the time being, just keep it off because you want to see whether it's read or write, and you want a 7-bit address. Because if you turn this on, you're getting an 8-bit address, which is just going to bugger you up. It's going to mess you up and confuse you. So I would just leave this off. So you're using a 7-bit address, but I'll show you in a subsequent slide. I'll show you what happens when that's on. And then if you hit the next page, you go to the next page, page 2 of 2, you could list you could go in here and you could scroll down through these. You're going to want to choose hex. You want stuff in hex. You don't want in binary or octal. You know, hex is so much easier to read. And you're going to want to trigger link to decode 1. So once that's done, that's it. Away you go. So here's the decode. So here's the scope decode of the proper device. So it's 0x3f. So I'm just zoomed in here. Okay, and I've just zoomed in here so you can see it here. So here, notice you've got everything captured on the screen, and the scope can detect the start bit, detect the stop bit, and it could decode this. Now, notice it's saying, you know, for capture number 1, it's I squared C, time was blah blah blah, it's address 3F, which is correct, read write is right, and data is AA, which is absolutely bang on. So you can see it's working. There's an automatic decode. Now here's a decode for when you turn this bit on. So if you set that, you know, that remember I was saying, you know, leave it on off. So if you put it on, the address now becomes 7E. It still knows it's a write bit and AA, but this is now telling you the address is 7E, which is not. It's 0x3F, right? And that's because it's included. This is how the decode was done before, with a separate write bit, but now it's including the write bit in the data, and so it becomes 7E. So now I'm just going to quickly touch on using a logic analyzer. Just got a couple of slides here, and then I'm done. So this is the logic analyzer I got. It's $10 off of AliExpress. I paid less than this because I got it probably about 5 years or 6 years ago. It's WEAC logic analyzer. It's based on blah 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 blah, and it uses blah 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 blah, and it's blah 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 blah. But it's 24 megahertz, 8 channels. It does 0 to 5 volts, and blah 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 blah, and yada yada yada. There's a address for it. You know, you could go and look at that on your own. Now this is using, I use SIGROC PulseView, and this is a free software you can get. It runs on Linux. It's a pain in the ass to get it to run on Linux. It runs on Windows. It's a lot easier to get it to run on Windows, and this works with that device. Now this works with only a handful of devices, so you got to make sure whatever device you get, if you're using PulseView, PulseView has a firmware for it, because what happens, PulseView loads firmware on the device to do the decode. So it's a free open source software, and blah 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 blah, yada yada yada. You could read this on your own. So this is how I got it to run on Linux. I had it running on Windows 10, but yeah, I guess about a year ago, almost a year ago, I migrated all my stuff to Windows, to Linux. I'm using VMs, and I used AI. AI was just helpful, but it was painful because it got everything wrong. It was 100% wrong. This is what AI told me to go and do, to set up some rules. It's 100% wrong. It didn't work. Finally, after much prodding of AI, I finally got it to say, okay, we're going to just override everything, and we're going to add a rule for that specific USB device, and we're going to load these rules for it. I'm going to apply, and we're not going to apply any of these other UDEV rules. And you have to reload the UDEV rules, blah blah blah, and run PulseView. As I said, it was a pain in the ass to get it running on Linux. But once you get it going, it's pretty straightforward. I know this looks gross, but you guys are still there, right? You're still with me?
Yeah.
Okay, so So when you go into pulse view, the first thing you have to do is you have to trigger what you're doing. So what I did was I connected ground. So if you go back to here, these pins are all labeled. G for ground. I don't know if you can see it. It'll have 0, 1, 2, 3, 4, and so forth. So 0 is, channel D0, D1, D2, and ground. So the first thing you have to do is connect ground to the test board, my little proto board. I connected ground. I connected D0 to clock, D1 to data, and then I go into pulse view. Once it's connected up, I start up pulse view, and I told pulse view for channel D0 I wanted to trigger on a falling edge. So here it is here. You can't really see it, but these are the conditions you can tell it how to trigger. So I told it to configure on a falling edge of D1, and D1 is data. Remember, we want to get that start condition. So you want the falling edge of D1. And then once you do that, then you go in and you select add a protocol up here. You select this window pops up, you select I2C, and then in the window, there's a decode at the bottom, I2C decode, and you have to click on that. Then you have to define that D0 is your clock and D1 is your data line. This is really, really important. It will not work unless you do a pre-trigger capture ratio, and I'll show you what that is in a second. If you don't set this, so what it does, it says start capturing 10% of the data before the actual start conditions comes in. If you don't do this, it will never work. So here, down here, see it says I2C bits. So if you click on this, I2C, if you click on that, that's where you define your pins to say D0 is clock, D1 is data. If you click on D1 here, if you click on this D1, the trigger menu will come up, and you can see it's set for falling edge. So here, if you look, notice you could clearly see the start condition there, and you can see a gap here. So this allows pulse view to actually know when the start condition is. Unlike the scope, for unknown address, it picks it up. This is the known address. So this is 3F and AA. So there, it's decoding it. It's telling you 3F and AA. This is really helpful if your devices are communicating and you want to see if they're communicating back and forth. Like suppose this here you were requesting some data, and then following here you'd see the data coming back from the device, and you could see if the device is returning the correct data. So this is what this program is really helpful on. So here's a zoom in. I just zoomed in, and you could go through and you could actually manually decode this yourself, but it automatically decodes it, tells you here's your address bits, which is 3F, write bit is 0, and there's an acknowledge, and here's your data, an acknowledge, and a stop bit. It puts P for stop, because S it's got here for start, P for stop. Unlike the scope, this will capture when your device does not answer, when you get a NAC. So here you see the address, 13 hex. Remember in my little program I had it write out a bogus address, 13 hex. You can see nothing on the bus, acknowledges it, and you get the NAC. So unlike the scope, this will decode when the device is not present. So in summary, we're all done here. So when you're troubleshooting I2C, if you don't have to really go through a scope decoding it, just use the I2C scanner, right? That'll tell you if the device is on the bus. If you scan the bus and the device appears, okay, I got the right clock speed, I got the right pull-up resistors, everything's working, it's good news, right? Now, if you see an ACK, if you're manually decoding and you see an ACK, that's the same as scanning. You're saying that's going to rule out many of these issues. It's working because the device is answering. The bad news is if you see a NAC, that tells you nothing. It's just saying the device didn't answer. Is it because you had, the wrong address, the pins cross, your wrong pull-up resistors? That's not telling you anything. It's just telling you you've got a hardware issue. So if your SCL or SDA pulses are not square, then it's most likely pull-up resistors, or your bus capacitance is too large, so you got to adjust your bus capacitance. If you don't see any clock or SDA pulses, then you've got the wrong pins. Somehow you're probing the wrong pins. And so that's it, and let's take some questions.
Anybody got any questions for Dave? Go ahead, Pete.
Yeah, thanks, Dave. I will say, I when I started to have the problems, I went through that manual, and then I viewed a couple of videos, and then I went to Siglet and viewed their video that Jason had made. I still didn't get it to work. I went to AI and still didn't get it to work. And I can't remember now what it was, but when you sent me the email and said go through these different steps, there was one thing in there, and I can't remember what it was now, and that was the big difference. So I thank you for that and the way it worked. One thing I was going to say, what is the maximum length, Dave, for a bus for I2C?
Google's your friend. I have no idea.
Okay. All right. And one other thing that I'll comment, and then I'll turn it back, is I had a bit of trouble setting the voltage levels to trigger on. I could set one not too bad, and then the other one was a bit of a problem, and I adjust the positioning of the traces, and that I could get a little bit more level out of the voltage level out of it to where I needed it. But sometimes I just couldn't quite get up there. So I'm not too sure what was going on with that. Have you ever had any trouble setting your voltage levels at all, Dave?
Yeah, I've got the same problem Charlie has with his scope, where some of the knobs just turn and nothing happens.
No, no, I'm not referring to that. I'm referring to it just doesn't want to adjust up there.
Nope, never had a problem.
Okay. All right, thanks, Dave. That's great. I enjoyed it.
Anybody else have something for Dave? No, I guess not. Okay, Dave, that was good. I want to watch it again. So once you get it posted on your channel or wherever you're gonna post it, I'm gonna take a look again. Okay, so what would you guys like to do? Should we just do a round table, or do you guys have any questions, or want to talk about something in particular?
Do the round table and see what crops up.
Yeah,
we can.
Okay. So looking at my screen, I'm first. Oh, go ahead, Howard. You're muted, Howard.
Mistake.
Go ahead.
I pushed it by mistake.
Okay. So since I'm the first one on my screen, I'm going to go ahead. Last month or so, I haven't been doing much. Got back from 10, 11, 12 days of camping on Sunday? No, Saturday. We were supposed to stay till Sunday, but they were calling for 3 to 4 inches of rain and severe thunderstorms on Sunday while we were camping, so we decided just to leave a day early. Previous to that, I decided to try and build a wire vertical antenna for field day over at Eric's place. Um, I think I was pretty successful. It was supposed to be good for 40 down to 10 or up to 10, and I was hoping to get the higher end of 80 on there to tune, but that never worked out. But in general, I think it was Saturday. I think it was Saturday morning. I don't know. Correct me, Eric. I did a couple of DX contacts on this wire vertical I put together, and
Yeah, well, I know you had some receive only, I think, from Europe, right? But you actually, I think, made some confirmed like two-way contacts within North America. So yeah, it worked.
Yeah, it was working good. It was working good. And I think I used it with my my Scout right at the beginning. No, actually, we set up Eric's radio and his sloper, multiband sloper, and but later on, when I brought it home, I did set it up quickly in the backyard, and it was working pretty good. 40 to 10, I was under 2 to 1 without a tuner, and that was using a 4 to 1 on. But I think I've got enough information and screen grabs and everything. I might try and put a presentation together and do a presentation about it later on. I plan to continue working with this. I live just down the street from in Brampton, from the park where Park has their field day. I might set something up there and just to try it out. But other than that, nothing else going on right now. Next on my screen is Al. Go ahead, Al.
All right. Well, like you said, I'm kind of about the same. I joined you up at Eric's. That was a lot of fun, Eric. Thank you. I was only there for the afternoon, though. Other commitments. It was my first chance to test out my Pac-12 antenna, so that went fairly well. I was also using my Z-Bit-X for the first time. It was interesting. I wish it was a little more sensitive. I really wasn't overwhelmed with signals on field day, but anyhow, that's what it was. Eric, just for your information, you were trying to get onto the lower bands with your buddy pole antenna. I did make up some adapters for the whips I've got from metric to imperial. So if you want to give those a try again, let me know. They're sitting here available to you.
Great. Yes, thank you. I'm sorry. I know you sent me a email about that, and it got buried in the deluge. But yes, thank you so much. We'll next time I'm down in Mississauga, maybe I'll bring my buddy pole and we'll give it a shot.
Sure. Yeah, glad to see what I can do, because these whips I've got are quite long, but seeing as they came from AliExpress, they all had metric threads on them, and the buddy pole was manufactured in the United States. So it's got all imperial threads. So adapters required. So anyhow, we got those made. Not much else going on, just plugging away. It's summertime, as we all know. Right now, the only thing I'm starting to play with right now is I need to make myself a return loss bridge for my Sigilant spectrum analyzer. So I'm looking at the one that we did with the Park VNA. I think that circuit came from experimental methods in electronics. So I'm looking at that, thinking, well, how can I modify this or make another one? But fairly basic. But just another accessory for the essay. I've got a friend that's going to come over and wants to characterize a few things, so that's what we're up to. Apart from that, nothing else to report. It's summertime, it's hot, and I'm not spending a lot of time in the shack. So that's it, Ken. Back to you.
Yeah, that's that time of the year. Get outside. Next on my screen is Dave. What you been up to besides your presentation?
If I can find my mute button. Yeah, no, not much. I've got a couple of weeks. I'm going up to Timmins to judge a rocketry competition. So I'm reading through students' reports and getting ready to go and judge a whole bunch. There's about 40 kids launching rockets, upwards to 100,000 feet. So I'm going up and I'm participating in that as a judge. So that's what I've been doing.
Yeah, good stuff. Good stuff. Drew, what you been up to?
Well, I am doing a little radio. Usually this time of night, and earlier in the mornings, I'm doing a lot of FT8. I have had kind of good luck. Just adding to the list, I got the Congo and a few others that I really didn't expect to get. I've been tracking that one for about a year, so that was fun. On another note, I was playing around with RM Noise some time ago. It's an AI-based noise reduction system. And I had good success with it about 2 weeks ago. I haven't had a computer in the shack that would run it. And I recently got gifted an Acer laptop that will run it. And yeah, it allowed me to get into Slovenia. There's a fellow over there, S50DX, I think it is. And one of the local fellows here talks to him quite often, but I've never been able to get through. Even though his signal's very good, my noise levels tend to be close to where his level are, about S9, S8. And with this thing, I was able to get through very nicely. So that's been one of the. Other than that, I'm working a lot on my boat, and so trying to get a lot of projects that I wanted to get done, years ago. Recently retired in March, so now I am doing all kinds of projects and finishing them up, and the boat has been the primary focus. So that's summer for me.
Very good. So when you have your boat launch, you're gonna call us over for a party?
Oh, it's in the water.
Oh, it is. Oh, okay.
Oh yeah. No. This is all stuff. Without any requirement at all, I have put instrumentation on the boat. Just because, and getting it to work with the software has been kind of interesting. It's a NEMA 0183, it's the old HP bus. And so hooking them all up in through serial ports and converting that USB has been a bit of a challenge, but I've got that handled. So I'm sure there's lots of packet collisions going on because it's a very unbuffered bus. But full instrumentation now, including depth, all being sent to the laptop, which is kind of fun.
Drew, how many radios on the boat?
As many as I can put on it. I can run, Ken Scout is a good radio to use on there because 50 watts is a good, you don't want to be putting too much power out because the batteries aren't that strong. But 50 watts, no problem at all. And I do actually take Meshtastic down with me just to see if I can hear myself. And so far, no. So I actually have to hoist the Meshtastic node up the mast. And I'm only 2 kilometers away from my house, maybe 3.
Huh.
And I'm not receiving anything down there. So I'm thinking, okay, well, that's not great. Anyways, I have done some work with the Meshtastic recently. But the boat itself, I have run, I ran a field day off it once.
I mean, you have marine radios on the boat, I presume, right? Or a marine radio?
I do, and one of the instrumentation hooks I did was to I have a GPS signal on the NMEA bus, so I wired it up to put that into the radio. So I have received GPS into the radio. So if things go badly, it has the magic red button, and you press the red button, and it screams for help, and then sends your GPS location.
Nice, nice.
But I have a really old Marine HF rig if you want it. It would satisfy the requirements for anchoring without much problem.
How many people fit on your boat, Drew?
Well, depends on whether they're friendly or not. Maybe 4.
Okay.
It's a 25-foot sailboat. It does not have a high coach. It has a lower. So if you're camping in it, it's a great deal like camping in a half ton. But it's it's old. It's 1960, I don't know, 3 or 6 or something. No, in fact, nobody knows how old it is.
You said 25-footer?
Yep.
Yeah. Okay.
Yep.
Very cool.
Yeah, no, it's fun. It's a toy. This is how I amuse myself. I sit down there and watch the swans kick the crap out of the Canada geese, and interspersed with that, I've put lazy jacks on the sails. I put all the instrumentation is up and running now. I've made sure the motor is reliable, which takes a bit of playing around with. I actually played around with a big electric trolling motor I bought a decade ago. And my next electric project is going to be looking at the controls of it, because it turns out this thing will actually push my boat. It's a 12-volt, but it's an older trolling motor, electric.
Right.
And it actually seems to have, it has absolutely enough thrust to move the boat around, which shocked the hell out of me.
It sits on the bow of the boat?
Well, no, actually, I have to rig something on the ladder for it to hang off of.
Okay.
And the controls are pretty flaky. I think I have to look at it again, but as I recall, it's some kind of wafer switch. I'm not maybe switching coils in and out. I'm not really sure why you would have that on a motor like this, but it's got detents, and they really don't feel particularly good. So I want to go in and clean that up before I rely on it. But I tested it actually this week, and just hooking it on the side of the boat, and it pushed the boat. And I thought, wow, that's quite surprising. So when docking, this would be very valuable.
Oh, nice.
Yeah.
Well, I have very limited experience with trolling motors, but what I do, the controls always tend to be a little flaky. So.
Well, this thing's it's kind of scary. It doesn't spark, but it feels like it's grinding a little bit. Like I have to take the head off of it and take a look at it and see what's going on. I had to spin the head around on it anyways years ago, because it was built as a trolling motor for the bow. So both the prop and the controls were on the same side. So I flipped it around to the other side. But I remember at the time thinking the controls seemed a little hokey. And it must be 20 years old.
Yeah, but some of this older stuff is built better than what you can buy now.
Well, and I expect it can't be anything terribly serious. I mean, I don't even know if it has. I can't understand why anybody would be switching coils in and out on an electric motor that's running off a DC. But maybe that's how they control it. I'm not sure. So me and Dr. Google will be finding out exactly how one controls these motors, and maybe building an alternate control system, maybe just relays or something.
Yeah.
Just because if it's going to be a reliable source of propulsion in low speed situations, I would like it to be reliable.
Yeah.
You know.
Understandable.
But it's a toy. You know, I'm just goofing around here.
Cool stuff, Drew.
That's fun. I'm just coming to grips with retirement, Ken. I gotta tell you, it's a different world.
I wish I could have that different world.
You will.
Eventually. Okay, cool.
All right.
You're next in line there, Eric.
Okay, the only thing radio related that I'm doing, but it's on a daily basis, is practicing my CW. So hey, there's something. Using my little Morse code tutor thing, and actually, I've pretty much got like perfect transmission now on what I'm sending. Receiving, still a work in progress, but sending, I'm pretty good. I'm just practicing essentially. Contest exchanges, that type of thing. But getting pretty proficient with the good old iambics. So anyway, practicing. Yes, the amplifier circuit is sitting right beside the paddle. So I kind of look at it as I'm keying away. So I key dot it dot it C and dit for an E and dit da for an A, and common emitter amplifier. Is that count as far as working on the project? I don't know. Anyway, yeah. So not to worry. It is actually, it's out on the table and ready to rock and roll. So next is finding the little bits and pieces I need to actually finish the job. So anyway, that's about it. Otherwise, it's been a very musical summer so far. I've been to like 4 music festivals and camps and what have you. So that's been taking a lot of my time. Different type of frequency work. So there you go. Back to you.
Very cool. Next in line, I see Michael. What you been up to?
Yeah, I'm here. I should be anyway. Yeah. I haven't really been doing very much. I haven't had my radio on and haven't been doing any DXing for a long time. I did I did take my QCX up to Earl Row twice. First time I got there, discovered that I left my paddle at home. So that was the end of that. And later in that week, I also discovered I didn't have my headset. So that was a bit of an abortive try. It was a 40-meter QCX. I was all set up to put up my antenna and everything. And then 2 weeks later, we went back up, only to find that on the side of the campground, the side of the campsite, there was a power line, which I hadn't realized was there. So discretion was the better part of valor. So I didn't set it up because I was concerned. Who knows? It might have fallen into the power line. Anyway, so that was that. Otherwise, Wayne Harrison and I have been fiddling around with with crystal characterization. We bought 100 crystals and we ended up characterizing them for the series frequency. Got all that done using Wayne's spectrum analyzer, and I've had abject failure in terms of using the scalar network analyzer, the SNA, to do anything. So we're going to have another crack at it. And Peter, maybe at some point, Wayne and I and you can sit down in a Jitsi session and figure that out. Anyway, I spent a few days with Eric, with Wayne fiddling around with that, and we're getting there very slowly. And Wayne is also doing the same thing that Peter's done, talking to, I guess it's ChatGPT rather than Claude, about how to make sense of the results we're getting. So that's really where we are, and maybe next week I'll get back to it. We have visitors this week, so I haven't had much of a chance to do anything. And about the only other thing is I've made up a set of parts for myself, Kevin, Charlie, and Wayne for the superhet receiver parts, and also the LNA analyzer, no low noise amplifier parts. Those are all ready to go. We're waiting to get our crystals characterized so we can put 4 sets of crystals together that more or less work, and then gotta mail those out, and then everybody will have the stuff for the superhet receiver, I guess. And that's about where I am. Yeah. Nothing else really.
All right, very good. Pete, you're up next.
Okay. Well, I've spent a little bit of time, not enough time, trying to configure the controller to work with my Superhet board. I did have it actually working, but I was not happy with the crystal filter, so I rebuilt the crystal filter, changed it up a bit, and it works much better. But I haven't configured the controller yet to match it. I was having a lot of problems with band switching on the board, and that's what got me involved with the I2C decoding with the scope, and that took up an enormous amount of time. And then Dave came in with the rescue, and I was able to see it. And actually, what it turned out to be was the Pico. It has two I2C lines, or ports, I guess I should say. And one port was working fine for the SI5351, but the other port, which was controlling the filter board, was not. So the fix was easy, but it took me a long time to get there. Of the last couple of weeks, I've been spending a fair bit of time with continuing work on my spreadsheets for crystal characterizations. One is based on using the SNA as the source of the data, and the other one is from the SA as the source of the data. I think I've come to the conclusion now, and as I posted the other day, Claude told me I've come to a conclusion in not so nice terms, or I should say, not in quite those words. So I won't go into that here. It's just too much. Let's just say I could write a PH. Got my PH all done on that PhD. What else did I get going? I think that was about it. Yeah, that's about it for me, Ken. Thanks.
Very good. Let's see who's up now. Oh, Cherry, go ahead.
Yeah, hi everyone. Good to see everyone after some time. I think it has been 1 or 2 months now. So I've been on a trip, and then it got extended due to some reasons for a couple more weeks, and then I'm back now. Just catching up on work for the past 2-3 weeks, and nothing really, not much is going on. So I hope I will have better updates next time. Yeah. Thank you. Thanks, everyone. Good to see everyone. Thanks.
Very good. Very good. Hey, Bob, long time no see or hear. What you been up to?
Okay, yeah, hey guys. Yeah, I'm trying to get my shack together. You see a little bit of stuff in the background there. My packet tarpon node just crashed day before yesterday. I think the Raspberry Pi gave up the ghost, so I gotta hunt around in my junk box and find another Raspberry Pi 4. Drew, I just laughed when you talked about the swans chasing the Canadian geese. Please send some swans down here, because you guys are the Canadians I want. The geese are the Canadians I don't want. But also, when you retire, you'll find out that you have less time on your hands than you had when you were working. And some of you guys already realized that. What else has been going on here? Summers are different down here. You guys say that the summer is you're going to get outside. Well, we've had summer down here, and frankly speaking, you want to stay inside. But if it's not the heat, it's like the bugs that they have down here. And the mosquitoes are the least of your worry. They have these little, the southern is called the no-see-ums. Little bugs you can't see, but they sure hell bite the hell out of you. They've been eating me up, so I've been having to stay indoors most of the summer until the weather cools down a bit. Let me see, what else is here? I got most of my HF stuff working, and I'm now working on the QRP stuff. And then finally will be the UHF VHF. I built when you build a wire antenna, I made an 80-meter inverted V, and I have a lot of trees in my lot, and I got the center conductor up like around, I don't know, it's probably around 20 meters or so. And I got one of the legs down pretty well, but the other leg is snagged in a tree, and I got to get that other leg up there so I can get all the stations, but I have been able to get on the air with it. I also, when I got my general ticket down here, my first commercial antenna was an AP8A made by Cushcraft back in the, I guess, early 80s, late 70s. And it's a ground mounted vertical from 10 to 80. And it really works well when it works. And I've kind of slept it around from QTH to QTH. And now where I am here, I'm in a restricted community. So antennas are not supposed to be allowed, but I found 3 trees and I can hide it in the middle of those 3 trees so my neighbors won't be able to see it. But the problem is that I've been trying to tune it, and I've been having one heck of a time, but I can't get it mounted and tune the top section because it's too high. So I've been trying to tune it laid horizontally, and that doesn't seem to be working. So I think I'm gonna just have to get it up there. I'm gonna guy it to the 3 trees instead of to the ground, and see if I can get that working. We've been having my Atlanta club. We have a field day, we have a day in the field, second Sunday of every month. So I've been going out for that, and that gives me a chance to like experiment with other guys' antennas and play around with the radios. So that's been about it. So like the task in front of me, the next big task in front of me is to get this APAA up and off of my mind. Ultimately, I've got to clear my workbench table, which now is like a rabbit's nest, and I can't find anything in it. And also, I've, putting together the shack all together. I had everything in one room before, and now I've got things scattered in 3 different rooms. So it's been a bit of a headache trying to run back and forth. You need a screw here, and you run to this room, and you find that the screws are in another room, and the nuts are in another room, and the bolts, So it's been driving me crazy, but I'll get it, and ultimately I'll have something to report. So back to you guys.
Very cool, Bob. Yeah, I was camping roughly about last 2 weeks. Yeah, I know about the gnats. You call them no-see-ums. We call them the gnats as well. And both legs on the back, red spots all over the place.
Yeah.
Is that you posting on the QRP Labs? I see Bob Bennett all the time.
QRP Labs? Yeah, that's probably me.
Yeah, okay. Yeah, I thought it would be. Okay, so that's it. So the next meeting is September, where is it? September the 2nd, that's the mixer. And on the 16th is the main meeting. So I guess we've come to an end, and we'll call it a night, guys. Thumbs up. Okay, very good. So everybody have a good evening, good weekend, and we'll see you in September 2nd.
Thanks, Ken.
Yeah.
Sounds good.
See you.
All right, guys.
Thanks so much,
Bye.
Dave.
Night.